So yeah, today's our last lesson of the year, related rates. This is a lesson that probably could have come a long time ago when we initially learned about how to differentiate implicitly defined equations. But the calendar didn't really play out very nicely with that extra lesson and the testing and all that. So I think this will be a good review of implicit differentiation. And basically what related rates are these types of problems where you use implicit differentiation to solve what essentially boils down to a geometry problem, where different sides of a shape or different variables in an equation are changing at different rates. So before we get into all that, let's just kind of review how implicit differentiation works. It works just like regular differentiation, except for when you're differentiating with respect to a certain variable. If the variable that you're not differentiating with respect to, like consider this function up here, it's got x's and y's. If I differentiate with respect to x, which is what I usually do, I'm going to just differentiate each term in this equation. But when I get to the ones that have y, since y is not x, then we're going to have to use a little chain rule and treat y as like a separate function. So let's just see how that plays out. So if we take this equation, we want to differentiate it with respect to x. Just do one term at a time. Derivative of sine x is cosine x. All right, so that's no big deal there. But the derivative of y cubed with respect to x, we need to use chain rule on this. We want to be thinking about y as like it's a different function. So using the chain rule, we'll differentiate the something squared and get like 3y squared. But then we need to multiply by the derivative of y with respect to x. Now, the derivative of y with respect to x is dy dx. The reason why we don't have that over here is because when we differentiate x with respect to x, dx over dx, it's just 1, right? So you really do have a dx over dx right here. You just never write that, okay? Because the derivative of x with respect to itself is 1. The slope of y equals x is 1, right? So the derivative of x with respect to x is just 1. Okay, so each time you've got one of these terms that has a y, or really like any variable that's not the variable that you're differentiating with respect to, you are going to have that extra differential in your equation. So let's finish this one up. So equals, now the derivative of 6y is 6 times the derivative of y, which is dy dx. Okay, and then the derivative of 4x is just 4. Like I was saying earlier, you would have like a dx over dx, but that's just 1, so there's no need to write it. So this is how that differentiation works. Back when we originally learned how to do this, oftentimes what we would do is solve for dy dx, which says like what is y prime. You would collect all of your terms that have dy dx over on the left-hand side, move everything else to the right, and divide. We're not going to do that right here, but that's one of the things that we did back when we learned how to do this. So let's take that same equation just to really make sure we're understanding how this implicit differentiation works and differentiate it with respect to y instead of with respect to x. Okay, so this is a little different. This is not very typical that we would do this. But if we're differentiating with respect to y instead of with respect to x, we're going to get basically the same answer, except these will be like dy over dy's, which will be 1, so you won't actually write them. But the terms that have x will have a dy dx. Or, I'm sorry, dx dy. So let's just kind of roll through this. So the derivative of sine x is cosine, but since we're differentiating with respect to y, okay, we got to find the derivative of x with respect to y, which is not necessarily 1. Because the derivative of x with respect to y is going to be dx dy, the derivative of x with respect to y. Now, when we differentiate an expression that has y in it, you won't have that extra differential at the end because you'll have dy over dy, which is just 1. So here we just have like 3y squared for that second term. Let me move this over a little bit. All right, so derivative of 6y with respect to y will just be 6. And the derivative of 4x with respect to y is going to be 4 dx dy. Now, in part A, this extra differential that we have, like dy dx, what that represents is the change in y in terms of the change in x. But down here, this is the change in x in terms of the change in y. A little different there. Now let's do one more, but instead of differentiating with respect to x or to y, we're going to differentiate with respect to t, which is, for all the problems we're going to be working, going to represent time. So maybe you've got some equation like Pythagorean theorem, where you've got 3 sides of a right triangle, and the question is asking about how is x changing with respect to time? Like, what's the speed of the change of x? Or what's the speed of the change of y? Those may not be the same. In fact, most of the time they're not the same. Okay, so when we differentiate with respect to time, what we're trying to find is a speed, essentially, the speed of the change. So derivative of sine x will still be cosine x, but since we're differentiating with respect to t, that chain rule is going to give us dx dt, which is representing the change in x, the x value, with respect to time. Y cubed is going to be 3y squared dy dt, the change in the y value with respect to time. Derivative of 6y is just 6 dy dt, and differentiating for x with respect to t will be 4 dx dt. Any questions so far? All right, so the variable that you're differentiating with respect to is pretty important because that kind of changes your answer here. Most of the time, we're just differentiating with respect to x. And if you're using Lagrange notation like y prime, there's like an implication that you're differentiating with respect to x. That's why like the Leibniz notation dy dx, even though it's a little bit more cumbersome to write this a lot, actually gives you more information because it's explicitly telling you what you're differentiating with respect to. Whereas the Lagrange notation, it's just an implication, right? Like it's not telling you exactly what you're differentiating with respect to. It's just most of the time it's x. And if that's the only other variable in the problem, it's sort of safe to assume that. But when you start having like multiple variables in here, then it becomes a little bit more important to use this Leibniz notation. Okay, so let's look at one problem that we'll have to differentiate with respect to t, and then we'll start talking about how this is all going to come into play with the related rates problems. So here we want to determine dx dt. So this is what we're trying to find, given these other pieces of information about x, y, and dy dt. Dx dt is referring to the rate of change of x in terms of t. In other words, how is x changing over time? Dy dt is how is y changing over time. So let's differentiate it with respect to t here. We'll do basically what we did on the previous problem. Okay, so we'll have 3x squared dx dt. Now for this next term, we have a product, so we'll have to use the product rule. It's been a little while since we did product rule. So as a little reminder, if you're trying to differentiate a product, it's the derivative of the first function times the second plus the first function times the derivative of the second. Okay, f prime g plus fg prime. So for this term right here, this 2x squared times y, what I'm going to use for f is the 2x, and the second function is y. All right, so I'm just going to kind of go through the product rule here. So f prime g, so the derivative of 2x squared would be 4x dx dt. So that's just this piece. Maybe I should highlight that just to be very clear here. Okay, times g, which would be the y. Okay, so that's the first part of the product rule. Second part of the product rule would be 2x squared, that's the f, and then times g prime would be dy dt. So all of this is the derivative of this term right here. The next term is minus 4y. So the derivative of that's just minus 4. Okay, but we're going to have this dy dt due to the chain rule. And what's the derivative of negative 2? 0. Yeah, derivative of any constant, slope of a horizontal line is 0. So yeah, 0 ddt, 0 times anything, 0, so we don't need to write anything else there. Okay, so here we're trying to solve for dx dt. So I'm going to isolate that variable. To do that, I'm going to move, or I really don't need to move any terms, but I'm going to leave the terms that have dx dt over to the left, and then these other two terms that don't have a dx dt, I'm going to move to the right. So I've got 3x squared dx dt plus 4xy dx dt equals 4 dy dt minus 2x squared dy dt. Now at this point, I've got two dx dt's. I'm trying to isolate that, so I need to factor those out as a greatest common factor, the dx dt. I'm getting a little closer here to our answer. And you can factor out the dy dt if you want. It's not really necessary for this problem because we're just going to be plugging in a number into it. But that's something that we did pretty frequently back when we implicitly differentiated before. Again, not really necessary because of what we're doing here. I'm just going to leave it as is. Okay. Yeah, last step here to find dx dt is going to be divide everything by 3x squared plus 4xy. Okay, so we've isolated dx dt, but this particular problem gives us values for x, y, and dy dt. So we can plug those in wherever they belong, and then we'll have our dx dt. So first, I'm running out of colors here. You got x equals 5, so I'm going to plug that in here, and here, and here. Okay, I've got y equals -1. So So I'll plug that in just right here. And dy dt is 2. So this 2 is going to go right here. All right, so I'm just going to make those substitutions and then do a little arithmetic, and I'll have my answer. So 4 times 2 minus 2 times 5 squared times 2 all over 3 times 5 squared plus 4 times 5 times negative 1. That's basically your answer. I guess we could simplify this a little bit. If this were a free response question, you'd be done right there. But if this was multiple choice, you're going to have to go a little further. So I've got 8 minus, what would that be, 25. 25 times 4 is 100. And on the bottom there, we got 25 times 3 is 75 minus 20. So negative 92 over 55. Yeah.
When you're doing the free response on the AP exam, like, how do you know how far to go?
Basically, like, once you've substituted all your numbers in, you're done. So, like, if it's just a matter of doing arithmetic, you don't have to do that. So, but this would be like the first time you would be totally done. This step right here.
You put the second step in here to solve for it, which is so great.
Say that again.
Yeah.
Like if you plug it in here, what are you saying? Or what are you saying?
No, like, would any of those three answers that are all like clustered together at the bottom work?
Yeah, any of these are fine. The only reason I went further than this is just because if this is a multiple choice question, your answer is going to look like this. But if it were free response, then I would just be done with this expression. All right, any other questions about that one? All right, let's get into the good stuff. Now, the kind of problems we're going to solve today are called related rates problems. And typically the way that you go about solving these is that you set up an equation. Most of the time, although not always, it'll be some kind of like geometric formula, like area of this, volume of that, distance formula, all these different formulas. And then you're going to differentiate with respect to time. That's like the overall gist of what you're going to do for most of these problems. So let's just go through some area and perimeter, circumference, all these formulas, just to make sure that we know what they are. Because some of these you'll be expected to know, although some of them, and I'll tell you as we go, you won't be expected to know. But for now, the ones that up front here, you're going to need to know, for instance, area of a square. Okay, so how do you find the area of a square? Yeah, but it's a square. So, oh no.
Length square.
So in a square, the length and the width are the same number, right? So in other words, like, let's say, on your coordinate plane, I draw a square. So all I need to know to find that area is x, right? I just need to know one of the sides. So the area here is x squared. Now, if I differentiate this with respect to time, it's going to give me a formula that describes how the change in area is related to the change in the side length. So in other words, let's say you want to know how fast is the area growing if the side length is growing at 2 meters per second. That's what that derivative formula is going to give you. So if I differentiate this with respect to time, I'm going to get the derivative of area with respect to time equals 2x times the derivative of x with respect to time. In other words, however long the side length is, the rate that the area changes depends on x, but is also related to the rate at which the side length is changing. So, for example, let's say you had like some square that's growing at a constant rate. Let's say that constant rate was 1 meter per second. What this gives me is how fast the area is changing based on how fast the side length is changing. Now, what's also kind of interesting here is it also depends on what the side length is, which means that the area is changing at a different rate for each individual side length. Okay, we're not gonna like solve the problem with that yet, but just want to kind of explain what's going on with that equation. It's just literally relating the two rates of change. That's why these problems are called related rates problems, because they are relating two different rates of change to each other. All right, what about perimeter of a rectangle? So same idea here. Let's say we have a rectangle. Probably not a square, although squares are rectangles. But with a rectangle, you're not guaranteed that the side lengths are the same. So you're going to have like x and y here. Right? So how do I find perimeter of a rectangle? No, perimeter, not area.
Y x squared. Length squared x less y squared.
Okay, hold up. Y'all, what does perimeter mean? Well, let's back this up a little bit.
Y plus 2y.
Yeah, perimeter is just the sum of all the side lengths. Ooh, okay, I didn't think we had to go that far back. Yeah, that's okay. Perimeter means the sum of all the side lengths. You just add up all four side lengths. So there are two x's and two y's. Now, if I differentiate this with respect to time, I'm going to get dp dt equals 2 dx dt plus 2 dy dt. So the perimeter is going to change based on how fast the x and the y sides are changing. Yeah. Any questions so far? All right, let's keep going here. Area of a circle. All right, what's our formula for area of a circle? This one, hopefully you know. Hopefully better than the perimeter formula. Yeah, pi r squared. This is still one you've got to know. This is not going to be one that's given to you on the test. So if I differentiate this formula with respect to time, I'm going to get the change in area over time equals 2. Now, pi is a constant here, so this is like 5r squared. You know, it's obviously not 5, but it works the same way in terms of the differentiation process and the power rule. So we got 2 pi r times dr dt. All right, what about the circumference of a circle? Do we know that one? Oof, man, we need to go back to geometry, I think. 2 pi r. Okay. Huh, interesting. So we've seen that somewhere before, yeah? Maybe that's related to the area? No? Okay, so the circumference is 2 pi r. And if we want the speed at which their circumference is changing with respect to time, the derivative would be 2 pi, that's the coefficient, times dr dt. All right, Pythagorean theorem. Now I know y'all know this one. This is the one formula everybody knows. Hopefully you know this one, but usually you talk about Pythagorean theorem in terms of A, B, and C, but instead I'm going to write this a little differently. I'm going to write this kind of like how you would have experienced it in trigonometry or pre-calculus. Okay, where we have x, y, and r for the hypotenuse side. Okay, this is also the distance formula. If that was never like brought to your attention that the distance formula literally just is the Pythagorean theorem, well, I don't know what to say about that. Yeah, the connection probably should have been made a long time ago. So anyway, Pythagorean theorem here is x squared plus y squared equals r squared. And so if I want to know how these variables are changing related to each other, differentiate this with respect to time and get 2x dx dt plus 2y dy dt equals 2r dr dt. Then we've got our trig functions. And we're not going to go through each individual one of them. It'll take too long. But if this is x, y, and theta, okay, what's the like? Let's set up. How do I want to write this? You know what? I think it might be easier to just write out the actual formula, like the function here, like f of x equals or y equals. So let's say we want to do y equals sine theta. Let me erase this. All right, now what's the derivative of sine? Cosine, okay. So we'd have dy dt equals cosine of theta d theta dt. Or if you had cosine as your function, it would work kind of similarly. You'd have dy dt equals negative sine theta d theta dt. We're not going to go through the rest of them, but just wanted to show you a couple of examples here. All right, volume of a cube. Now we're getting three-dimensional here. All right, so not only do we have like a square base, but now we've got like depth to this shape. Okay, now with a cube, all the side lengths are the same. So if one of the side lengths is x, then the volume would just be x cubed. Thank you. And the derivative of this with respect to time would be dv dt equals 3x squared dx dt. All right, volume of a sphere. This is one you don't have to know. Okay, you do not need to memorize volume of a sphere. If this is ever one that's given to you on the AP test, you don't have to know this formula. They'll give it to you. Okay, so I'm just going to give this to you. The volume is 4/3 pi r cubed. And props to you if you remember that from geometry. So a sphere is just like a three-dimensional circle, just so we're clear. Yeah, I can't really draw very good, but I'm trying to get some dimension on there. Okay, so volume of a sphere. So if the radius changes, so will the volume. And so if we differentiate this with respect to t, we're going to know what that relationship is. So dv dt, the change at which the volume, or the rate at which the volume is changing, is equal to 3 times 4/3, which is be 4. So 4 pi r squared dr dt. Area of a rectangle. All right, so let's go back to rectangle. And I know we struggle with the perimeter on this one. But what about the area? How do we find area of a rectangle? Yeah, length times width, right? Yeah. Just multiply the dimensions, x times y. So yeah, area is x times y. So if I differentiate this, I'm going to have to use the product rule. Okay? Product rule again is f prime g plus fg prime. In this case, x prime y plus xy prime. So the derivative of x with respect to t, or I guess we got to do a first, would be dA dt. Okay, now we're going to do the product rule here. F prime g plus fg prime. So derivative of x with respect to t is just dx dt times y plus f times g prime dy dt. If I can just make that blue. All right, volume of a cone. This is another one that you'll be given. You won't be given the derivative formula, but you'll be given like the actual formula for volume of a cone. So you don't need to memorize this first formula, 1/3 pi r squared times the height. But you will need to know how to differentiate that with respect to time. Okay, a cone, by the way, looks something like this. So the height is here. Radius obviously is there. Okay, so let's differentiate this. We are going to have to use product rule again. So dv dt with my like quote unquote f being 1/3 pi r squared and my g being h. So the derivative of this first part is 2/3 pi r times dr dt times h. Okay, so that's the f prime g plus fg prime. So plus 1/3 pi r squared times the derivative of h with respect to time, which is dh dt. Whew. All right. And I just realized there's one missing on here. I'm going to throw one more at you. Volume of a cylinder. Okay, this is another one that, even though you probably should know because we've done a bunch of cylinder problems already, in this case, I think volume of cylinder is going to be one that sometimes is given to you as well. So it's pi r squared times the height. So if we differentiate that with respect to t, we're going to get, let me just kind of block this off here, dv dt, and we're going to use product rule one more time. 2 pi r dr dt h plus, maybe move this down here. It's going to let me, no, once, okay. It's all right, I'll just erase that. There we go, we'll put this down here. Plus pi r squared times dh dt. All right, so these are like the most common formulas that are used in these related rate problems. But as we go through and solve some of these, basically what we're going to be doing is setting up one of these equations. And then like we did back here on this problem number 2, within the problem, they're going to give us some information about the variables that we need to know to find whatever it is that they're asking for. So it'll be like, usually it's like, find the rate of change of x, given x, y, and change in y, or something like that. Now, before we actually get into these problems, one more thing. I want us to just kind of practice writing or identifying what is the piece of given information here using the calculus notation, using the d over d notation, the Leibniz notation. So the first one says the radius of a circle is growing at 3 inches per second. Okay, so if it's growing at 3 inches per second, that is a rate of change. So this means that the dr, which is the radius, in terms of time, is growing at 3 inches per second. So that's how you would write that. And if they give you information about the rate of change of something, that's going to be one of those differentials. Okay, if the perimeter is shrinking at 5 feet per minute, that means the perimeter is changing at a rate of -5 feet per minute. Because it's shrinking, it's getting smaller. If the area of a circle is increasing by 5 square centimeters per hour, that's the change in area with respect to time. If the horizontal distance between two people is decreasing, they're walking towards each other, then the change in x with respect to time will be 2. All right, so these are just like some quick examples of like what you're going to be looking for in the problem and what they represent when we set up our equation. All right, any questions at all before we start digging into the actual problems? I kind of laid the groundwork here. Okay, let's put it all together. All right, so this one says the radius of a circle is increasing at the rate of 3 inches per second. At what rate is the area increasing when the radius is 5 inches? Okay, so what formula are we going to start with here? Area, perimeter, circumference, volume. Like this is part of the process, is identifying like which geometry formula am I even talking about here? So maybe take a moment to reread the problem. The radius of a circle is increasing at a rate of 3 inches per second. At what rate is the area increasing when the radius is 5 inches? So from all those geometry problems we just wrote down, all these formulas, which formula do you think is the most relevant to this problem? Area, yeah, area of a circle. Okay. And what's given is the rate at which the radius is increasing So this is right here, our dr dt. It says, at what rate is the area increasing? So what this is asking is, what is dA dt? What does that equal? dr dt is 3. What is dA dt? When the radius is 5 inches. So the radius is going to be 5. So let's start with kind of the known geometry formula. All right. the area of a circle is pi r squared. If we differentiate that with respect to time, we get dA dt equals 2 pi r dr dt. And now we've got, if we look back at what the problem gave us, they gave us the rate of change of the radius and the current size of the radius. In other words, they gave us these two unknowns that we're going to use to calculate the rate of change of the area. So the rate of change of the area with respect to time is 2 pi times 5 times 3. And then we just simplify. So 5 times 3 is 15, times 2 is 30. So the area is changing at a rate of 30 pi square inches per second.
For this one, why would you have to do like 3x or something? Like, because
Say
you're
again?
finding it like right at that one time.
Right. So with these problems, like everything's changing, right? And so basically we're like hitting the pause button on this thing that's changing and wondering like what's going on at that moment. So yeah, like the radius is changing, but it's saying right when the radius is 5, what's the other two rates?
Why is it inches squared?
Because it's an area. So area are always going to be squared distances. So like if it's a distance, it'll just be like a distance unit, like inches, meters, whatever. If it's an area, it'll be like square inches, square feet, square centimeters. If it's volume, it'll be cubic. So basically that exponent is just describing how many dimensions to the shape there are. One dimensional, like a line, will be like centimeters, a distance from A to B, right? An area has 2 dimensions, length and width. Volume, 3 dimensions. So, yeah. All right, let's do another one. An inflating balloon. So air is being pumped into a spherical balloon at a rate of 8 cubic inches per minute. So this 8 cubic inches per minute is the change in volume over time. Find the rate of change of the radius. Okay, rate of change of the radius is dr dt when the radius r is 2 inches. So the geometry formula we're going to work with here is given to you. Yeah, the volume of a sphere, the volume is 4/3 times pi r cubed. But we've got information about like the rates of change, right? So we need to differentiate this with respect to time. dv dt equals 4 pi r squared dr dt. And so what it's asking for is the rate of change of the radius. And so basically we're going to have to solve for that variable. Right? They give us the rate of change of the volume, right? And so it was 8. They give us what the current radius is at that moment is 2. And that's all you really need. Okay, dr dt will equal dv dt divided by 4 pi r squared. And those two variables are given. So at this point, it's just a matter of like plugging them in the right spot, and then you've got your answer. So we have 8 divided by r is 2. So 2 squared is 4. 4 times 4 is 16. So 8 over 16 pi, which would reduce to 1 over 2 pi. Now, usually on these problems, they're going to ask for the units as well. So this is a rate of change. It's how the radius is changing over time. Radius is a distance. It's one-dimensional. So it's just going to be inches per unit of time, which in this case was minute. So inches per minute. Any questions about number 5? All right. Now, this problem is probably the most common one that I've seen. I see this all over the place, many, many years going back, is this classic ladder problem. Okay, where basically a ladder is leaning up against a wall, and then the bottom of the ladder starts sliding out from underneath. So the question is asking, like, how fast are you falling at any given time? Like if you're at the top of the ladder. So it says a 6-meter ladder is up against a wall. So let's draw a little house here and get your artistic. So here's the house. Yeah, put some details on here. Yeah, it's like a house that my little daughter would draw. Okay, we've got the ground. Yeah, and then the ladder, which is up against the wall. All right, so it says that the ladder is 6 feet, or sorry, 6 meters. So we'll go ahead and label that. All right, so it says, let's keep reading here. If the bottom is pulled away from the wall at a constant rate of 5 meters per second, all right, so this is like our X, and here's our Y. So if it's being pulled away, the bottom down here is being pulled away. As this is being pulled away, the top of the ladder is sliding down the side of the house. So the rate of change in the X direction is 1/2 meter per second. So that's our dx dt is 1/2. How fast is the top of the ladder sliding when it reaches 5 meters up the wall? So this would be our y value is 5. All right, now this is a right triangle, right? And so we're going to set up the Pythagorean theorem. We're going to differentiate it with respect to time. And then we're going to plug in everything that we know, and hopefully we have enough information to be able to solve for how fast the top of the ladder is falling. That's our dy dt. Now, just to make sure we kind of understand this conceptually a little bit, if the side of the ladder, the part of the ladder that's touching the wall, if it's sliding down, what kind of answer should we be expecting here? Like in terms of the speed. If it's going downwards, it should be negative, right? Yeah, the speed is negative, the position's decreasing. Okay, so let's set up our Pythagorean theorem here. We've got x squared plus y squared, bring that up a little bit, equals r squared. And we're going to differentiate this with respect to time, because over time, these things are changing. So we've got 2x dx dt plus 2y dy dt equals 2r dr dt. And now let's just start plugging in everything that we know, and if there's anything we're missing, we'll come back to it. All right, so do we know how far at this moment, when the y distance is 5, do we know how far away the bottom is from the wall? How far? Oh, so you don't know.
Well, I know how to find it.
Okay, yeah, even better. How do you find it? You just use Pythagorean theorem, right? So like as of now, this x value isn't known, but we could draw a little triangle down here where the y is 5 and the length of the ladder is not changing. That's going to be a constant 6. And then so we need to find the x at that moment. And so we're just going to do a little Pythagorean theorem here. Okay, if this is x, then x squared is going to be 6 squared minus 5 squared. So x is the square root of 36 minus 25, which is 11. Okay, so that's my x here, root 11. Yes, ma'am?
So like whenever you put like dx over dt, like why do you have to do that? Because normally we don't have to do that. Even when we do like
Because usually what we're doing is we're differentiating with respect to the variable that's there. Like if I want to find, let's just say like the derivative of 2x, right? Well, like usually, like before we start getting into implicit differentiation, we would just say this is 2, right? The derivative of 2x is 2. But that's because we're differentiating with respect to x. Even if we use the chain rule in the same way, we would have the derivative of x with respect to x. You could, I suppose, write dx, but anything divided by itself is 1.
Is that not usually dy over dx?
It's not. It's usually dx. So anyway, that's why. So here we're differentiating with respect to t. Now, if one of these variables was t, when you get a dt, you wouldn't see that written. Okay, so we've got 2 root 11 times dx dt. Okay, how is the x value changing? It's increasing. Okay, give me that increase. What is the rate specifically? 0.5. Good. So that's going to be a 0.5, or I'll just write it as 1/2 plus 2 times y, which is 5, times dy dt. That's actually what we're trying to find, right? This is our goal, is to find this dy dt. How fast is the y changing? Okay, equals 2 times the length of the ladder, 6. How is the length of the ladder changing? It's not changing, right? It's always going to be 6. The ladder isn't like magically shrinking or anything. So the rate of change is 0. It's not changing. Okay, so this equation looks a little complicated, but really it's not too bad. I mean, everything's filled in. We just need to isolate dy dt. So just simplifying this a little bit, 2 times 1/2 is 1. So this is just going to be root 11 plus 10 times dy dt equals 0. There's a weird looking t there. Let's fix that. All right, then subtract the root 11 and divide by 10. We get dy dt equals negative root 11 over 10. And so it is negative, which is what you should be expecting because the height is decreasing. So the rate of change should be negative. And the units here are meters per second. So this problem is actually pretty common. Not like with the same numbers or anything, but this setup of you've got a ladder falling down, how fast is the ladder moving? Or how fast is the top of the ladder moving? Because what I think is like kind of weird, I always thought it was weird when I first was learning about this, is that the speed of x changing is not the same as the speed of y changing. I always thought that was kind of strange, but it is different. Okay, number 7. A coffee pot has the shape of a cylinder. Okay, good thing we talked about the cylinder formula. With radius 5 inches. Okay, so let's just start marking things down as we see them. This is our R. Let H be the depth of the coffee pot. Okay, so that's labeled already, measured in inches, where H is a function of time. The volume V in the coffee is changing at the rate of negative 5 pi root H cubic inches per second. Okay, so this is how the volume is changing. This is our dV dt. It's the rate at which the volume is changing. Determine the rate of change of the depth of the water when the water is 7 inches deep. So this is our H. Okay, now just going back to our formula for volume of a cylinder. Oh, actually, it's given, so we don't even need to go back. Volume equals pi r squared times H, the height. And I'm going to differentiate both sides with respect to time. So dv dt, and we've got to use product rule here. 2 pi r dr dt h plus pi r squared dh dt. So this is really just our classic product rule, f prime g plus f g prime. Now what we're looking for here, what the question's asking for, is the rate of change of the depth. Okay, that's our dh dt, the change in the height with respect to time. So hopefully everything else is given, and then we can just solve for dh dt. So let's just start plugging things in, based on what the problem gave us. So the dv dt, they didn't give us a number, but they did give us an expression here. Okay, -5 pi root h equals, that was the change in volume with respect to time, then 2 pi r, so r, the radius is 5, so 2 pi times 5 times the speed at which the radius is changing. Well, the config is just going up and down, right? The radius of the cylinder is not changing at all. The cylinder is not growing this way, right? So the rate of change of the radius is 0. Okay, times the height, which is 7. Actually, we could go back and throw in 7 in that other h. Let's change that to 7. Plus pi times the radius, which is 5 squared, times the rate of change of the height. That's what we're trying to find. We don't know that yet. But notice here that we've got everything else is filled in. There's no more unknowns. It's just going to be a matter of simplifying this equation and then isolating dh dt. Okay, so notice on this first term on the right-hand side of the equation, we've got a 0 as a factor. So that's just going to be 0, right? So I'm going to just rewrite this as -5 pi root 7 equals nothing plus 25 pi dh dt. And then I just need to divide both sides by 25 pi. So dh dt will equal -5 pi root 7 over 25 pi. That's it. And then you can simplify that a little bit, but that's basically your answer. Right? Pi divided by pi is 1. You can reduce. 5 over 25 would be 1 over 5. So our final answer here is going to be -√7 over 5 inches per second. And that is the rate at which the height is changing. Since that number is negative, that means the height's decreasing. Someone's drinking the coffee. Any questions so far? All right, one last problem. It says the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by the function r of time t, where t is measured in minutes. Okay, so we've got this notation, r prime. R prime of t, another way of saying this, using the Leibniz notation, is dr dt. Okay, just for reference, this is what we call the Leibniz notation. You don't need to know this by name. That's the Leibniz notation. This is the Lagrange notation. Okay, but you don't really need to know those names, just FYI. But they mean the same thing. Okay, so part A says estimate the radius of the balloon when t is 5.4 using a tangent line approximation. All right, this is like one of the first types of problems that we solved, like in the beginning of the year. It's like how to write the equation of a tangent line. And so even going back to like, August or September or whenever it is we originally learned about that, we need a point and we need a slope. If we have those two things, we can come up with our tangent line approximation. Once we have our tangent line approximation, we can substitute in 5.4 and get our answer. We're going to tangent line approximation. So the point is going to be t comma r, right? Time and the radius. The radius is in terms of the time. So at time 5, the radius, be careful here, the radius is not 2, because this is the speed at which the radius is changing. If you go back to the problem up here, it says the radius of the balloon is 30 feet when the time is 5. Radius of the balloon is 30 feet when time is 5. Okay, the slope, that's the rate of change. That is the dr dt. So the derivative or the rate of change of the radius with respect to time at time equals 5, that's where the 2.0 comes in. All right, so now we have all the pieces to write our equation. Y minus 30 equals 2 times x minus 5. This is a tangent line approximation for the speed, for the radius in terms of time. So if we want to be maybe a better way of writing this, instead of using x and y, is to write t and r, just to make a little bit more sense in context. So it says estimate the radius of the balloon when the time is 5.4. That's what we're going to put in for the time. So r minus 30 equals 2 times 5.4 minus 5. 5.4 minus 5 is just 0.4. So we have 2 times 0.4. 2 times 0.4 would be, hold on, is that right? Hold up. Yeah. 0.4 times 2 would be 0.8. And so if we add 30 to both sides, we're going to get 30.8. So 30.8 feet. All right, let's see if we can get this last problem. Still based on the same scenario here. It says find the rate of change of the volume. The rate of change of the volume is dv dt when time is 5. Indicate units of measure. So they give us the volume of the sphere is 4/3 pi r cubed. If we differentiate that with respect to t, we're going to get dv dt equals, what would that be, 4 pi r squared dr dt. We're searching for the rate of change of the volume. So that's actually already isolated. We just need to plug in everything that we know. We know the radius. At t equals 5. Yeah, it's the same problem, right? So the radius is 30. So 4 times pi times 30 squared times the rate of change at that time, which we already established up here, was 2. All right, so we got 30 squared. That's going to be a big number here. Hold up. 2 times 4 is 8. 8 times 900. Does that sound right? So we got That would be 7,200 pi cubic feet per minute. Any questions on any of these related rate problems? All right, these will take some practice, but the overall strategy here is to read the problem, try to figure out what formula it is you need to start with, whether it's area, perimeter, circumference, volume, whatever. Set up that equation, differentiate it with respect to time, and then go through the problem and try to pick out what pieces of information are given, plug those in to find the piece of information that it's asking for.